The other thing we need to talk about this week is testing equality of covariance. So we all should know that t-tests and their extensions, which we will talk more about in subsequent weeks, have certain assumptions. And so when generalizing to multivariate analysis, we've already addressed one of these back in lab 4. Anyone remember what that was? As a hint, we used blank's test for blank blank. What are those blanks? We used Marty's test for multivariate normality. So what's another assumption we can often check that we haven't discussed yet that's an assumption about t-tests? So here we have blank of blank. That would be homogeneity of variance, or in multivariate stats, equality or homogeneity of covariance. So the assumption is essentially that both groups are drawn from a population with equal covariance matrices. Last week, we also talked about how we could use likelihood ratio test based methods as a different way of getting our t-squared statistic. And this t-squared statistic is checking for equality of means. One of the reasons we like likelihood ratio methods, though, as opposed to, I mean, we like the t-squared method, but likelihood ratio methods we also like is because they tend to be very flexible. And it turns out we can actually use likelihood ratio based methods to test for that the two groups have equal covariances. So as in last week, we're using lambda as our sort of initial test statistic for checking equality of variances. And so here is the sort of general form for any number of G groups. Remember, we're focusing on 2 groups this week, so we may come back to this form that's for G groups, but this is sort of the original general form. And when we look at an example, we'll be focusing on 2 groups for now. But here we have this is the product of the ratio of the determinant of each group variance to the pooled covariance. So S sub L is the group is each group's covariance, and S pooled is the pooled covariance among all groups. And then we raise it to the power in each case of the proportionate to the sample size. So n sub L, which is the group sample size -1 divided by 2. And so note that especially when there are many groups, just in general, this is a complicated product formula. You're doing lots of multiplying stuff out. And there's actually a transformation in likelihood type analysis that's very common that helps us simplify this to something that's more computationally manageable. Has anyone seen anything like this before? So what's a common way we refer to a likelihood type statistic? So we often take -2 times the log of the likelihood, or in this case, -2 log lambda. And so you'll see this come up again and again in likelihood-based analysis, in likelihood ratio tests, in the information criteria like AIC and BIC. There's often this -2 log transformation. So the sort of important piece of this is this log piece. Can anyone see why taking the log would sort of benefit us computationally? And so one way to start to think about this is to think about what are our log rules and what do our log rules do for us? So the first one that we're going to look at here is the product rule. And so remember, for the product rule, we know that the log of x times y equals the log of x plus the log of y. So what that does is it allows us to change this ugly multiplication product symbol into a sum symbol. And really all we do is we take our log. So here we're multiplying everything, and we move the log inside, and we instead say we're adding everything. So we're adding the log of each element as opposed to taking the log of the product of each element. And so these are equivalent. So that's the first step. The next is the power rule. So the power rule is that log of x to the y equals y times log x. So let's just take this exponent up here and move it down to the other side of the log. And so here now this becomes a multiplication factor, which again is also a simpler computational procedure. So now we have NL -1 over 2 times the log of the ratio of the determinants. And so we have -2 times the sum of that. And finally, we have the quotient rule. So the quotient rule is similar to the product rule. It says that log x over y is actually equal to log of x minus log of y. So that allows us to take this ratio and turn it into a subtraction. So now we have n minus 1 over 2 times log of the determinant of S of the group covariance matrix minus the log of the pooled covariance, the determinant of the pooled covariance matrix. So we can also multiply out this -2, and that essentially gets rid of this denominator in the NL minus 1, and it leaves us with this. So we now have a sum of a fairly straightforward form. And so we can rearrange it just to look a little bit more straightforward. So now we have the sum of each group sample size minus 1 times the log of the determinant of the pooled covariance matrix times the sum of each group sample size minus 1 times the log of that group's covariance matrix. And that's our M statistic. And this is just the same thing as saying -2 log of lambda, which we saw before. So this is really just a straight transformation of lambda into M. And so this is called Box's M statistic. And so, as I said, we're going to look at the two-group case because it's a little bit simpler to compute, of course, and we're talking about t-tests, which involve two groups right now. So we can just plug in, take out so for this, we just take out the sum piece because we only have two groups. And we're just for each NL, we're plugging in 1 and 2. So here we have N1 plus N2 minus 2 times the log of the determinant of the pooled covariance matrix minus N1 minus 1 times the log of group 1 covariance matrix plus N2 minus 1 times the log of the determinant of group 2 covariance matrix. So M, also we need there's another step here. So M can be linked to a chi-square distribution to check if two covariance matrices are equal via this C to the C inverse transformation, or sometimes it's called U transformation. In the textbook, it's U. In the handout David probably gave you, it's C to the -1. Same thing, same idea at least. They're slightly different, but they wind up doing the same thing. So C to inverse is equal to 1 minus all this stuff, 2p squared plus 3p minus 1, and those are all constants over 6 times p plus 1. I don't know where these constants come from. I didn't prove this. I just know it works. And then times 1 over n1 minus 1 plus 1 over n2 minus 1 plus 1 minus 1 over n1 plus n2 minus 2. And so M times C inverse is then chi-square distributed with P times P plus 1 over 2 degrees of freedom. So note that this is an approximation, and it holds up best when each n is at least 20, and you have no more than 5 variables. And it's also very sensitive to violations of multivariate normality. So if you're going to use this, you should probably check multivariate normality first. And don't worry, in the homework, I'm going to show you how to program all of these formulas if you'd like, but for the homework, I'm not going to make you do this. We have a function that's going to do it for us, so don't get too scared. So first thing we're going to do is check multivariate normality. So we're going to use the weight height data again. So I'm going to check each group separately. So we want each group to be multivariate normal on its own. So here is for female. So we have pretty high p-values for both skewness and kurtosis here. Then for male, once again, we have p-values greater than 0.05 for both skewness and kurtosis. So it seems like we can't reject the null hypothesis that either skewness or kurtosis violate normality. That's what we want to see. We're able to retain the assumption that these data might be drawn from a normal population. So for M, we need all this stuff. We need N1, N2, so that's the sample size of both groups. That should be S1 and S2, so that's the covariance matrix of both groups. This typo, it should be covariance 1 and covariance 2. And then we need the pooled covariance matrix, and we'll also need P. So this is just the same as what we've seen before. I think I did this in exact procedure in the last slide. I'm just not showing every step here. I'm just obtaining each of these and giving them a name. That way that my code is nice and generalizable. So now I can basically just plug everything into my M formula. So I just plug everything in as, you know, exactly as I named it. So this is just literally the programmed version of this formula where my variables are named as the variables that I want them to be. So we get my M statistic, which is 10.95. So now I need to get C inverse, and same thing. I've got all this stuff programmed. So this is literally just the programmed version of this formula, and we see this is is a modifier that's very close to 1. So now we get our test statistic, MC inverse, and so that's going to be, because C was so close to being 1, that's going to be it turns out to be very close to what just M was. And then we get our p-value from our chi-square distribution with p times p minus 1 over 2 degrees of freedom. And so that's p 0.12. So in this case, we reject the null hypothesis that our two groups have equal covariances, which is technically a violation of our equality of covariance assumption. So of course there is a nice function. There's probably more other ones, but this one I found in the Heplots package. So it's called box M, and we see it gives us the exact same result. It gives us our chi-square and our p-value. And so we reject the null hypothesis of equal covariance matrices. We can also use the formula syntax to get the same result. So if we look back at the group level covariance matrices, we actually see that don't look super different. I mean, we see that the variances are a little bit larger for group 2, which is men, as are the covariances, but you know, not hugely different. So M is a very sensitive test, and a lot of times our t-squared is going to be fairly robust to violations of this assumption, but it is technically an assumption that we're holding, so we should know how to check it. And sometimes you'll just want to check. You may want to test equality of covariance matrices for other reasons as well. So this is how you can do it.